Hello, I'm Mirdad Simkhani, your college algebra professor. And in this lesson, we are studying the natural, exponential, and logarithmic functions. This graph is the natural exponential function. This is the graph of the natural exponential function, which we express as e to the x, if my pen works, y equals e to the x. The base e is a number approximately 2.7. This number, the number e, cannot be expressed as a finite decimal, and it cannot be expressed as a fraction. So it means that it is not a rational number. Also, it cannot be expressed with a formula that uses the four basic arithmetic operations plus root finding, square root, cube root, and so on. That means that it is not an algebraic function, algebraic number. We cannot solve an algebraic equation to have e as an answer. So e is not a rational number, is not an algebraic number, and it's called a transcendental number. Any number that's not algebraic is called transcendental. This other graph is the graph of what we call the natural logarithmic function. And we express that as y equal to ln of x. L for logarithm, n for natural. And as you notice that these two functions are inverse functions of one another. They are mirror images of each other over this line, the line y equal x. So one is a reflection of the other along this line. And this is the line y equals x. And what we can notice is that, which is based on the meaning of inverse function. For example, this point is 0, 1. That's the y-intercept of the exponential function. If you switch the 0 and the 1, we get 1, 0, and that is the x-intercept of the natural log. So more generally, when we have v equals e to the w, that's equivalent to saying w equals ln of v. So the input for the exponential function is the exponent w, the output is v. These two input outputs are reversed when you look at the inverse function, which is ln. ln of v, v is the input for ln here, and the output is w. So to see this on the graph, for example, if I pick a point like this point here, if I label it as wv, w being the input, v the output, x and y, then by reversing the two, v comma w, I get this point. And that point is on the natural log function v comma w. So this helps when sometimes we know v, for example, and we know it's equal to e to some value, w. The question is, how do we find that w? We find that w by using the ln function. So we input v into the ln function, and then we get the w out of that. Let's look at an example. So we want to solve this equation for x. We have e to the x equals 5. So the answer is simply x equals ln of 5. ln of 5 cannot be simplified, and you don't need to put in a calculator and give an estimate for it. The exact value of it is just ln of 5. Just like the exact value of e is e. E is approximately 2.7, and you can get more accurately by using a calculator with several decimal places. But we don't want to do that here. We just stay with the exact values of these values. So again, here x is the input, 5 is the output of that function, e to the x. When you reverse that, you input 5 in ln, and the output would be x. So that's how these two functions are related. They are inverses of one another. So here's another example. So we are solving this equation for x. So we want to know what x is. So this is ln of x equals 5. So we can just switch to the exponential function and say x equals the base of this logarithmic function. We will talk about bases later. Is e. So e is the base and the exponent is 5, e to the 5. And you don't need to put in a calculator. And that's it. That is the answer to this question. Here are some facts about the exponential and logarithmic functions. So for example, if you have ln of e to the x, because e to the x and ln of x are inverses of one another, here x goes into the exponential function and the output goes into the ln function. Because they're inverses of one another, ln will undo everything that e did to the x, so it gives you x back. So here's the same concept in reverse. X goes into ln, and then the result of that goes into the exponential function. An exponential function would undo what ln did to x, because they're inverses of one another, and you get x. If you input 1 for ln, ln of 1 is always 0, because that is because e to the 0 is 1. And ln of e is 1 because e to the 1 is just e. Anything raised to 1 is itself. ln of 0 is undefined because there is no way you can find, you can raise e to a number and get 0. E raised to any number will always be a positive value, regardless of what that number is, positive, negative, 0. So this is why ln of 0 is undefined. ln of negative numbers are also undefined for the same reason, because raising e to any number, it will never become negative. It will always be positive. And here are some other properties. Domain of the ln function is 0 to infinity. We just saw it above on the graph, you can see. And that makes the range of e to the x the same thing, because e to the x and ln of x are inverses, so the domain of one becomes the range of the other, and the range of one becomes the domain of the other. So the range of ln is negative infinity to infinity. Domain of e to the x is negative infinity to infinity. So those two are the same. Because e to the x is defined for any real number x. That's why its domain is negative infinity to infinity. ln of x has a vertical asymptote, x equal to 0. E to the x has a horizontal asymptote, y equals 0. You can see from the graphs, for e to the x-axis is a horizontal asymptote. As x goes to negative infinity, the graph of e to the x approaches the x-axis, and for ln, as x goes to 0 from the right side, the graph of the ln approaches the y-axis. So that's why the y-axis is the vertical asymptote for the natural logarithm. And that concludes this video.